Day 3. So today we're going to climb a little mountain. I hope the air is not going to get too thin up there. The slides are already on the website, so you can download it, especially if you sit in the last rows and you might not see all, especially the lower part of the transparencies, then you can, as I said, you can upload them. I mean, don't get scared. I mean, the slides that you find under the first talk today, actually, all the slides we're going to do, right? So we're not going to go through 65 slides in 1 hour. So it's for 4 hours, but still going to be interesting. Oh, come on! You're not so easy to be scared. So anyway, so this is what I roughly have in mind. First, I want to talk about Bayesian inference in general, because that's basically what's behind almost all the algorithms we do in data assimilation. So I want to say a few general things that I feel are relevant to the field of data assimilation. So that's the first hour. The second hour is going to be specific to data assimilation, because that's a particular type of Bayesian inference problem. And so that comes with particular issues and, again, things we need to worry about. And then in the afternoon, we're going to look into algorithms. So I will first put the Ensemble-Kalman filter into perspective. You've been using this in the hands-on sessions and maybe also in your practical work already. And then in the last bit, I will talk a bit about extensions and sort of ongoing stuff, etc. Okay? Now, just to get for myself a feeling whom I'm addressing, can I ask you, who has a mathematical and a training in mathematics and, let's say, physics? All right. Well, at least a few. Okay, so geoscientists. Geosciences? All right, okay, another third about, a bit more. And all the others, I suppose, come from other areas like biology, cognitive sciences, potentially. Yeah. Or just one? Did everyone raise the hand? Did I lost one community? No. Okay. The other thing is, why are you here? Are you here because you want to just use data assimilation as a tool, not just. I mean, it's an amazing tool, but you primarily have other scientific goals in life. That's option A. Option B is that you don't have to raise your hand. Listen to the options first, and then you can raise your hand. Okay, option B is that you want to learn about data assimilation because you want to apply it to areas where maybe it's not yet used. So you definitely have to know a little bit about the algorithm to adjust them to your needs. And the third option is that you really want to develop new data assimilation algorithms. So now, this was A, B, and C. So who is primarily in A? Just a very few. Okay. B, probably the majority. And C, who really wants to develop new algorithms. Okay. Right. It's not too bad. That's a good spread. But anyway, so as I said, it's going to go through some of the foundations. I hope I'm going to be gentle. To make this all work, of course, you have to ask me questions if you can't follow or something is not clear from the notation, because I live in it, and so for me, most of it is sort of hopefully clear. But I'm aware that, of course, for you, a lot of it will look different, to say the least. Okay? Right. Greg started a little bit of background, so you maybe also want to know a little bit about me. I'm an electrical engineer by training, but then I moved towards mathematics. And so I've seen both sides. So, in general, I try to combine practical stuff with theoretical understanding as much as possible. And today I will put primarily my mathematical hat on. But I have interest in numerical analysis, broadly speaking. Early on, I did a lot of work on Hamiltonian dynamics, a field completely separate from this here. So I was interested in celestial mechanics, like predicting the motion of planets, which is fairly well predictable. But you need clever numerical methods to do this for long times. And then I moved into molecular dynamics, and that got me into statistical physics. And then I did a couple of years in the UK, and when you move to the UK, you do fluid dynamics. And I got also interested, I've always been interested in weather predictions, so I got connected to the UK Met Office, and then they kept telling me I should really start working on data assimilation because they told me, is the most important field. And was about 10, 15 years ago. Initially, I was listening to talks on data assimilation. I had absolutely no clue what they were talking about. But eventually, it dawned on me. And so since then, I've been really hooked, and I think it's a fascinating area because it links so many interesting areas of mathematics, and it has obviously a lot of applications. And so I've written a little book a couple of years ago, which hopefully serves as a good introduction to the field. It came out at Cambridge University Press. Now this year, we've been successful in receiving funding from the DFG, the German Science Foundation. So we have now what's called a collaborative research center. That's like the largest scale funding the German Science Foundation has. It's a very nice funding because it can run up to 12 years. It's a lot of money. It's really meant to build at the university where they establish such centers to build a center in this area. And so it implies a lot of support. We have 12 scientific projects, a number of doctoral, postdoctoral positions, and we have little spring schools and fellowships and visitors program. And so let me know actually if you try to connect with us. I mean, there's a web page. It's still a bit under construction, but please talk to me if you like to. And the aim of it is sort of similar to the school here because what we're trying to do is to link the theory. So we have statisticians on board. We have people from machine learning, stochastic analysis, applied mathematics, et cetera. But we also have people from the cognitive sciences, biologists, few geosciences, but we're primarily interested in branching out to new areas of applying data assimilation, which I find is very interesting and very rewarding. Anyway, so this is a bit for the background. And now let's move into the subject. Now, data assimilation has really been driven by meteorology and the geosciences, also in oil reservoir, history matching, et cetera. And they've done a great service. I mean, I talked to people in stochastic analysis because there is sort of the field of filtering and smoothing. We will come back to this later, which is sort of the mathematical equivalent of data assimilation. And basically to them, in the late 90s, early 2000s, they said, well, it's pretty much we've done what we can do, and the field is dying. And some people, younger people, were leaving the field and saying, well, let's go into financial mathematics, et cetera. But simultaneously, basically, the whole field was exploding through the application in meteorology. And I guess mathematicians would have said, no, you can't possibly do this. I mean, it's impossible. But obviously, there is options. I mean, there are possibilities of doing it. And now we're trying, as mathematicians, I guess we're trying to understand why these methods work, what are the features, what are the common grounds of these methods. And of course, we're not just there to clean up, sort of, to come in the morning and be the cleaner. But I think it's really essential if you want to use these methods in other areas that you see what is the essence of it and how do you need to adjust them to do it for other applications. So that's at least my motivation. OK. Right. So part one, Bayesian inference. I think the words have already come up. So we're talking about a prior model. And here I mean by a prior model, it's a measure of probability density over some variables you care about. That can be the states of your model, but it can be something else if you care about something else, right? So it's a probability distribution. And it's your prior belief of what these variables of interest, how they distribute it. And then you have data, so that's the likelihood. And then you combine this prior information with the likelihood, the measurements, to get the posterior, right? Okay. And when I started out in this field, I was still in London at Imperial College, and that has a very strong statistics department. And I got constantly asked, or I was involved in this in this debate. Are you a frequentist or are you Bayesian? I mean, for statisticians, this is sort of the most important question, right? Are you Bayesian or frequentist? I mean, and so in a nutshell, a Bayesian person is one that treats everything as a random variable, whereas a frequentist says, well, the variable we try to estimate is actually a fixed quantity. It is a number, right? So we want to estimate a number. So it doesn't treat it as a random variable. I think Bayesian world has now taken over, but if you talk to statisticians, I mean, they often will still, I mean, but there are a lot of, I mean, I don't want to get into this discussion, but if you talk to statisticians, you will eventually have to take sides, and you will have to understand this. Anyway, so I mean, I believe mostly in this room we are, in practice, Bayesianists or whatever. I don't know how you want to call them. Anyway, so if you treat any variable as a random variable, we need to understand what it is. So now I'm not going to go through the strict definitions, don't worry. So a random variable has a distribution. And normally you write it down, you have your Gaussian, let's say, and so your distribution looks like this, right, of your variable of interest. So here's your variable of interest. Let's call it Z. And that's your Gaussian distribution. And that would be what I denote by P. Now, we also talk about measures. And then we use this capital calligraphic P. Now, why do we need this, right? It seems like a bit unnecessary abstraction. So now one reason why we need it is that if you shrink this Gaussian and you make the width narrower and narrower, so the variance goes to 0, then the area underneath has to stay constant, is 1. So that means that the whole thing gonna go higher and higher and higher. And eventually you get something you probably see in the Dirac delta measure, or the Dirac delta function, right? And it basically says that all the mass is concentrated at that point. Now, when we do statistics, then we generally not directly may be interested in this density, but by expectation values. Expectation values are integrals. So basically, what we ultimately do, or we're talking about, is integration in various forms. And so if you have such a density like a Gaussian, and you want to compute the Gaussian, the expectation of G with respect to this Gaussian is a standard integral. So that's it. Now, as I said, if you move this down and you went to this Dirac delta, which is, let's say, centered about this Z0, then you can still write this expectation as an integral G of Z, and then we have this Dirac delta. But this is not really a function anymore, right? Because it goes to infinity. Of course, we used to this and we use this notation, it's all fine. But if you want to be proper, then you should better use this notation and center this distribution and write like this. Of course, this would not be a good reason to introduce this notation for you. And just the other reasons. The other reason is if you go to high dimensions. So let's say we take this vector Z now, we take it as a vector with components Z1, Z2, and you keep adding components. So you make this vector longer and longer. And each component is distributed Gaussian with mean 0, so it's centered, and the variance sigma I squared. So you get this enormous vector of IID distributed Gaussian random variables with potentially different variances. Now, so that this whole thing makes sense, we assume that you can sum these variances up. So as you increase the length of this vector, the sigma i's are chosen so that it gives a finite sum. And let's call it R squared. Right? You make this thing longer and longer, but you keep you keep the sort of the sum of these sigma squares constant. So now, let's look at the length or the norm squared of this vector and its expectation value. So what do you get? What is the expected length of such a vector? So you're summing the squares of IID Gaussian random variables.
0?
No, you square. I mean, if I would take the z's and just take their value and sum it up, the expectation value is 0 because they're all centered. But if you square them and then sum them up,